What's up, everybody? Welcome to part 2 of lecture 21. It's over section 4.1 and 4.4. That said, I feel like I should take a minute to stop, put on the brakes, and explain something, because some of you might be looking at the notes, doing the same thing I literally just said. Asking yourself, where the hell is section 4.3? Yeah, I accidentally forgot to separate 4.1/4.4 from 4.3. So, when you're going through your notes, you're going to find section 4.3 is at the end of that collection of notes for 4.1 and 4.4. That said, section 4.3 will be the subject of the next lecture video. So with having said all of that, I wanted to start off today's lecture with a quick definition, because we're going to be using this from now on. It's the idea of integrability and what it means for a function to be integrable. Now, if a function is integrable, what that means is at most, your function only has a finite number of jump discontinuities. For those who don't remember what a jump discontinuity is, a jump discontinuity is a discontinuity in your function, kind of like this, where it quite literally jumps. That's all a jump discontinuity is, right? And given that at most you have a finite number of these on a closed interval from A to B, then we say our function is integrable on that closed interval. In other words, the definite integral of your function from A to B exists. And that's all it means to be integrable. So if there's at most a finite number of these types of jumps, then this bad boy is going to be integrable. Now, having said that, the next thing I want to talk about that I'm going to erase the board and get into is going to be an example where we use series to actually figure out exactly what the definite integral is. But there's some notes that I'm going to skip over in the lecture video before I get to that example. So I'm just going to skip over a slide in the notes. And the reason why is because, one, I think it's something you need to look up yourself. It's not going to effectively do you any good for me to just put those notes on the board and be like, these are blah, 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 blah. What they are properties of sums and the sums of different powers. So it gives us a way of playing with series. So like I said, I'm going to skip over that part of the notes because I don't think it's going to do you any good to have me just write it out on the board and be like, this is the thing. Instead, what I want you all to do is to look at those, go back to your notes, pull off that PDF, print it out, do whatever you have to, but have it to the side while I go through this next example, just so you can see what's happening where. This next example is actually directly out of your notes. And the first thing we're going to want to look at when looking at this example is whether or not this example is integrable. So with having said all of that, let's check out the example. So for this first example, what we want to do is we want to find the definite integral from 0 to 3 of the function x cubed minus 6x with respect to x. That's what we want to evaluate. In order to do it, let's recall from the last lecture that if our function is integrable on some interval from A to B, then this definite integral is going to be equal to this Riemann sum, this right-hand Riemann sum, right? Now remember, we could use the left Riemann sum, the right Riemann sum, or the midpoint rule. Doesn't matter. All that really matters is that it is one of these Riemann sums, and we can show that this integral is equal to that series. And this is, of course, where delta x is equal to b minus a over n, and x sub I is equal to that a value plus I delta x. Okay. So again, this is a right Riemann sum. We could have used a left, or we could have used the midpoint rule. All those would have worked. Maybe would have caused a little bit more work on our part, but this will work, right? This is, of course, true. So, if that's the case, looking at this, there's two values that we can start to work out right away. We can start to say, all right, well, we know delta x is equal to b minus a over n. We don't know what n is, but we know what b is. B is 3, and a is 0. So delta x is just going to end up being 3 over n. Well, given that, then we know that x sub I is equal to a plus I times delta x is 3 over n. Now this is the dummy variable, or the dummy index rather, I, not the imaginary number I. So keep that in mind. This is not the same number, this is not the same I as the square root of -1. This is just a placeholder. It's a dummy variable, dummy index. So now, putting all of this together, we know that the integral from 0 to 3 of x cubed minus 6x, integrated with respect to x, is equal to the limit as n goes to infinity of the series from I equal to 1 up to n of our function evaluated at a plus I over 3n times 3 over n. Okay. So now we can start cleaning some of this up a little bit. Notice one of the things we can do is pull out that 3n, because it's a constant value in terms of the series, right? It never changes with each term. It stays the same. So we can treat it like it's a constant in that sense and just pull it out, because it's something that is shared with each term. It just doesn't change according to the series. So we can pull that up front to get this is equal to the limit as n goes to infinity of 3 over n times the series from I equal to 1 to n of our function evaluated at a plus I times 3 over n. Our function is this thing, right? So we could say, and we will say, we are saying, that this integral is equal to the limit as n goes to infinity of 3 over n times the series from I equal to 1 up to n of our first term in our function is going to be x cubed. Well, we're saying x is equal to this a plus I times 3 over n. So this is going to be a plus I times 3 over n. Just to clean this up a little bit, let's write I in the numerator that's cubed, minus 6 times, again, the same thing. And now I'm going to erase some of this out of the way, so I can actually write the rest of it out. So now we have 6 times the quantity, a plus I times 3 over n. Now, we're going to evaluate that beast. And I promise it's not going to be as bad as you might think. So I'm going to go ahead and give you a second to look back at those notes to find that table I was referencing, because we're going to need that now, just so we can evaluate this. Cool, while you all are doing that, I'm going to pause the video and clean up the board some. So for this next step, I went ahead and did a little bit more work in advance. What I did was first, I said, hey, our A is equal to 0. So we can just get rid of it, right? Yeah, just throw it out. Then I said, well, according to the properties of series, we could break this up into 2 other series, right? We had to, however, remember to distribute 3 over n to both of those series. And of course, since we're applying the limit to all of that, we need both of those series inside of one set of parentheses. That way we can say we're distributing, or applying rather, the limit to both of those. So from here, the next step, for some of y'all may be obvious, for others it may not. The next step here is just going to be to work out what's going on inside of both of these series. So, doing that really quickly, this is all equal to the limit as n approaches infinity of, well, we're going to keep that 3 over n times the series from n, or from I equal to 1 up to n of well, in this first term, we're cubing everything, right? So we're going to have I cubed times 27 over n cubed. Okay, I'm going to write that as 27 over n cubed, all that times I cubed. And you'll see why in just a minute. It'll make sense, I promise. And of course, we're going to subtract all of this from it as well. That's 3 over n times the series from I equal to 1 up to n of 6 times all of this. Well, 6 times all of this is just going to end up being 18 over n times I, right? Yeah. So we're going to write it as 18 over n, all that times I, close our square bracket, and then close our parentheses. Now, you may have noticed something here. In both of these series, I separated, in some sense, what changes term from term to term, or what changes by terms, from what just stays the same, right? This 27 over n cubed always stays the same for every term. However, the I cubed changes for every term in this series. Similarly, 18 over n stays the same for every term in this series, but this I changes for every term in the series. So, what we're going to do next is distribute those to their according 3 ends. In other words, we're going to have 27 times 3 is 681 over n to the 4th. And here we're going to have 8, 16, 24, plus 30 is 54 over n squared. And we're going to pull that out front for both of those series, just so that we're left with terms only in terms of I to the interior of those series. You'll see what I mean in just a second. I don't think I can write it over here, so I'm going to erase everything. We'll be right back with it. All right, so where we left off with that last bit of the example was with this step right here, right? And I had said, notice that 27 over n cubed doesn't change in any of the terms for that first series, and 18 over n doesn't change for any of the terms in this series. So for that reason, we can pull them both out. And when we do that, we're going to get these coefficients of 81 over n to the fourth power in front of this first series, and 54 over n squared as a coefficient in front of that second series. So that leaves us with our first series being of just I cubed, and our second series of just being of I, and both of them are from I equal to 1 up to n. Now what? Well, you could sit down with pen and paper and actually figure out what those series become up to some n value. Or you could look at that table that I was referencing and say, hey, this thing is equal to the square of n times n plus 1, that quantity, over 2. And this series is n times the quantity n plus 1, all over 2. Now from here, there's some rearranging that could happen. We could square everything in here, pull out the 2, which will at that point be a 4, right? And then distribute that into the fourth power n. When we do that, this is what our first term becomes. Similarly over here, we could just swap out the 2 and the n squareds and reduce everything down to this here. Now, we can actually evaluate this thing. Because check it out, in that limit, this term, 1 over n goes to 0, and this term, 1 over n goes to 0. So all we're left with in the end is that this thing is equal to any 1 over 4 minus 27. Just minus 27. Okay. And from here, you can evaluate the rest of this problem. And that's it. That's all there is to this. From here, like I said, it's just arithmetic, right? So there's not much else to be done. And that gives us, in the end, the answer to this problem. This integral is equal to 81 over 4 minus 27. Big look. Now, I'm sure some of y'all are terrified looking at this example that just took like, what, 3 board erasures and a lot of work. Probably looking at it like, oh hell no, I saw this in Stranger Things and it was terrifying. Yeah, okay, I'm sorry, I know. But it does get better. There are some tricks we're going to develop that lets us skip almost everything we just did. Just like there were some tricks with the derivatives that allow us to skip that limit definition. There will be the same thing happening for this stuff. So relax, hold on, it's not going to be that terrifying. That said, I do want to look at one more quick example because it highlights an idea that I have up to this point just kind of glossed over. and not even brought up. It's the idea of signed area and what the integral is, or what the definite integral is actually evaluating. Up to this point, I just told you it's some type of area. It's area. But there's actually a couple different meanings to that word, and one of them is signed area. So give me a second to erase all of this, and we'll see that example. A moment later. What's the deal with this problem? We're saying that integrals represent in some way this idea of area, but then we're saying that this particular example, you have to subtract this area from this area. Then it's not area, is it? Yeah, it is. It's a type of area. It's what's called signed area. And the reason why this signed area occurs is because of what the limit definition, the series development of the definite integral is. Let's go back to that limit definition, that series, right? We're taking these rectangles whose height are equal to the height of the function, right? In some way. We're defining it based on the height of our function. That's from this thing, right? That's what this f of x star sub I is doing. It's defining the height of each of those rectangles. But hey, notice down here, those heights are negative. So it's like this thing is measuring area, or at least a type of area, right? And that's because it is measuring a type of area. It's measuring area compared to its position on the x and y axis, compared to the region's position on the x and y axis. So if the region with which the area is being measured is below the x-axis, then it's negative area. If the region is above, then it's positive area. So when we say, what's the signed area from 0 to 3 of this function x minus 1, well, we need to subtract that region from below, or that region that is below, from the region that is above. That's it. That's all it is. But this also means if you want to know the area between the function and the x-axis, so not the signed area, but the actual area, you need to know when this thing is below the x-axis and when this thing is above. So there's some things happening here, right? If we want to know what that area between our function and the x-axis is, well, then we're going to have to find out what this area is, take that absolute value, and then add it to the absolute value of this area. And that gives you the total area between the function and the x-axis. However, if you are going to take the definite integral, then you're going to have to subtract this area from that area because this signed area is negative. And what the definite integral evaluates is the signed area between a function and the x-axis. Or in some cases the y-axis. We'll get more into all of that later. But for now, I wanted to make this point. Having said all of that, I have decided I am apparently again going to lie to y'all. This will not be a 2-part lecture, but a 3-part lecture. And the reason why is because honestly, already I feel like this lecture is probably going to be like 30, 40 minutes long. After another 40-minute long lecture, y'all aren't going to watch that. I know that. So I'm going to stop the lecture here and continue the last little bit in a 3rd segment. Because y'all are not going to watch another 40+ minute lecture. I get that. I don't blame y'all, especially after that last example we did that took like 4 chalkboards. That was crazy. So I'm going to stop it here, and we're going to come back to this in the next part of lecture 21. So part 3 of lecture 21. And again, for those who did not catch what I was saying at the beginning because you were skipping through the videos. Yes, I know you're doing that. I can see that. But for those of y'all who didn't catch it, lecture 4.3 notes are at the end of lecture 4.1, 4.4. I just forgot to separate those out. They somehow got mixed in. So the next lecture video will be finishing up 4.1, 4.4. Then the lecture after that, so lecture 22, will be going over 4.3, which is all over the idea of the fundamental theorems of calculus, which fundamental theorem of calculus says it all. It's the fundamental theorem of calculus. Know it, know it, know it, know it, know it. Lecture 23 is monstrous, it's huge, it's important, know it. Having said that, feel free to go. Have a good one, everybody.